Hi, this is Gio with class number 11 of the course Signals and Systems 2 at UPF Barcelona. I hope these videos are being useful to understand the fundamentals of signals and systems, and if you have any questions on the classes, feel free to get in touch. In the last couple classes, we learned how to represent the frequency response of a system in terms of its magnitude and phase with the so-called Bode plots. We also studied the behavior of first order and second order systems, their impulse response, their step response, and their frequency response. In this class, we will learn about sampling and reconstruction. That means representing a continuous time signal by its samples, which are its values at points equally spaced in time, and then reconstructing the original continuous time signal from its samples. Sampling is important as it plays a role as a bridge between continuous time and discrete time signals. In fact, the samples of a continuous time signal give the opportunity of representing it with a discrete time signal. When we take samples from a signal at a sufficiently fast rate, we obtain an accurate representation of the original signal. The same applies to the spatial domain. Think about a digital picture, which is nothing but a very fine grid of points, each corresponding to a sample of the spatially continuous scene in the picture. If the samples are sufficiently close together, then the picture appears as spatially continuous, even though it is not. The advantage of all of this is that processing discrete time signals is more flexible thanks to cheap digital signal processors. Therefore, if sampling is properly done, one can convert a continuous time signal to a discrete time one, process the discrete time signal through a digital signal processing system, and convert back to continuous time through reconstruction. So let's learn more about the first part of this process, sampling. So imagine that we want to represent a continuous time signal x of t through its samples. So t, for example, is our sampling interval, and we can correspondingly define omega s as 2 pi over t as the sampling frequency. A convenient way to represent this sampling process is by using a periodic impulse train that multiplies the continuous time signal that we wish to sample, x of t. So such periodic impulse train p of t, as described in the slide, is called the sampling function, and its period t is the sampling period or the sampling interval. So in the time domain, we have that xp of t, which is the sampled signal, is given simply by the product between x of t, the original signal, and p of t, the impulse train, which is the sampling function, right? So what we obtain in this case, since p of t is given by the sum of delta of t minus nt, it's an impulse train, the product between x and p will be given by the sum of x of t delta of t minus nt, for n going between minus infinity and plus infinity. So because of the sampling property of the unit impulse that we have discussed several times in previous videos and classes, we know that multiplying a signal x of t by a unit impulse samples the value of the signal x of t at the point at which the impulse is located. I guess we have repeated this several times and we should know this by now. So applying this property takes us to the last expression on this slide at the bottom, which is that the sample signal x of p is given by the sum of x of nt delta of t minus nt. The same thing can be visualized now with these pictures. So starting from the top one, the first plot is x of t, our original continuous time signal. Then just below we have p of t, which is an impulse train, and it's our sampling function. As you see, these impulses have unit amplitude and they are spaced by t, which is the sampling interval or the sampling period. When we multiply x of t and p of t, we get the figure at the bottom, which is a sequence of impulses located at integer multiples of t, and with amplitudes scaled by the values of x of t. So at point t equals 0, we will have an impulse with amplitude x of 0. At point t, we'll have an impulse with amplitude x of t, and so on and so forth. So this is the sample signal. Let's now look at the same procedure from the frequency domain perspective. So since xp of t, the sample signal, is obtained as the product in time domain between the original signal x of t and the sampling function p of t, then the Fourier transform xp of j omega in the frequency domain will be given by 1 over 2 pi times the convolution of the Fourier transform of the original signal x of j omega and the Fourier transform of the sampling function p of j omega. So if we write this in the form of the convolution integral, we get the formula at the top left of the slide, which is that xp of j omega is 1 over 2 pi the integral of x of j theta, where theta is just a mute variable, p of j omega minus theta d theta. So you see at the top right a representation, for example, of the spectrum of your original signal. This is just an example, it could have any shape. So let's take this as an example. So let's consider a signal which has a spectrum or a Fourier transform which is non-zero only between minus omega m and omega m. So we can regard omega m as the highest frequency at which the signal has energy, right? So what about the sampling function, p of t? Well, the sampling function is an impulse train, and if you recall from a previous class, the Fourier transform of an impulse train is also an impulse train in the frequency domain. Of course, the spacing is different, and if you recall, the smaller the spacing in time domain, the larger the spacing in the frequency domain, and vice versa. So in this case, we will have that p of j omega, the Fourier transform of the sampling impulse train, is 2 pi over t, where t was the sampling period, sum of delta of omega minus k omega s. That means replicas of delta of the unit of the impulse with an amplitude 2 pi over t spaced by a quantity omega s in frequency. Great. So what happens when we do the convolution between x of j omega and p of j omega? Doing the convolution between a signal and a unit impulse simply shifts the signal by a quantity given by the position of the impulse, right? So if we do the convolution between x of j omega and p of j omega, which is a train of impulses, this will give us a series of replicas of the spectrum x of j omega. That's what we see in the figure at the bottom right of this slide, and that's what we see in formulas at the bottom left. So we can look at the figure first, which is probably simpler. We see that xp of j omega, the Fourier transform of the sample signal, is nothing but a series of replicas of x of j omega. They are spaced by a quantity omega s, which is the spacing of p of j omega, which is the sampling frequency that we set at the very beginning. Their amplitude is correspondingly scaled. The same thing can be seen in formulas, as I said. Looking at the bottom left, this can be written as 1 over t sum of x of j omega minus k omega s. Those are replicas of x of j omega at positions k omega s, so integer multiples of the frequency omega s, which is the sampling frequency. That's great, because if you observe xp of j omega, you can see that in this particular case, the various replicas, we have infinite replicas, do not overlap with each other. That means that it is potentially possible to recover the original signal x of j omega by simply filtering xp of j omega. Imagine applying a filter that only preserves the central replica, that triangle in the middle, right in the middle, center at 0, and cancelling every other replica. We would just go back to x of j omega, apart from scaling coefficient, which is trivial, right? This is the case because the replicas do not overlap. So if you look at the frequency at which the first triangle ends and the second triangle starts, these are respectively omega m and omega s minus omega m. So this will hold as long as omega s minus omega m is larger than omega m. In this slide, again at the bottom right, you see a very different situation though. In this case, the same thing has been done. The original signal has been sampled, and in the frequency domain, its spectrum has been replicated. However, because of the sampling frequency value omega s, in this case, the replicas are partially overlapped. That's because omega s is smaller than in the previous example, and omega s minus omega m is actually smaller than omega m. That means that one triangle starts before the previous one has finished, to put it in simple words. So the result, xp of j omega, is a sum of replicas where a distortion has occurred. It's not possible in this case to recover the original spectrum by simply filtering xp of j omega, preserving one replica and discarding all the other ones. Something has happened. So that's what the sampling theorem tells us. The sampling theorem tells us under what conditions it is possible to recover the original signal after we have sampled it. This is a really powerful theorem. In particular, it says that if omega s, the sampling frequency, is larger than twice the maximum frequency of the original signal, omega m, then there will be no overlap between the replicas and perfect reconstruction will be possible by filtering xp of j omega. You see this represented again. It's just the same figure we saw before, just for you to realize that what counts here is the relationship between the bandwidth of the original signal, so the maximum frequency omega m, and the frequency at which we sample such signal omega s. So omega s has to be at least twice omega m. On the other hand, when omega s is smaller than omega m, and in some cases even when it's equal, that would not be enough, we have overlap. This phenomenon is called aliasing. We will see better why aliasing is an appropriate name. In this case, perfect reconstruction is not possible. So as we already saw, replicas overlap, and it's not possible by simple filtering to reconstruct the original signal. Some information has been lost, and some information has been lost because we have not sampled at a frequency omega s sufficiently high. For that reason, we have lost some information. So the frequency 2 omega m, which is the minimum frequency at which we should sample a signal that has bandwidth omega m, is called the Nyquist rate. Let's now talk about reconstruction. So how to recover the original signal assuming that we have correctly sampled such signal, assuming that sampling has occurred at a sufficiently high frequency. We'll see that perfect reconstruction is possible in that case, following the sampling theorem, but also in some cases imperfect reconstruction might be desirable if it is good enough, just because it would be simpler. The first example we'll see is what we can call band-limited interpolation or reconstruction. We say interpolation because this is basically a way of combining the different samples to make a continuous time signal out of them. So imagine that again we have the sample signal xp of t given by the sum of x of nt, the samples, times impulses delta of t minus nt. Its Fourier transform is represented once again on the right of this slide. So it's given by a series of replicas of the original spectrum x of j omega at distances omega s in frequency. So as we said, if we're given such representation, intuitively the way to recover the original spectrum, which is the triangle centered around 0, would be to simply cut off all the other replicas. And the way we would do this would be in the frequency domain through a perfect rectangular filter that has unitary gain around our triangle and zero gain outside in the stop band. Doing that corresponds to multiplying by a rectangular Fourier transform in the frequency domain, and in the time domain corresponds to doing the convolution with the anti-transform of such a rectangular function, which we know from previous classes it is a sinc function. Therefore, the operation we're looking for in this case for perfect reconstruction is a low-pass filtering that uses h of t, impulse response, omega c t sine of omega c t over pi omega c t. Basically, it's a sinc function, right? So it's obvious what we would do in the frequency domain, meaning rectangular filter multiplying in the frequency domain, but in the time domain we see the same thing represented at the bottom left of the slide. So it's a convolution. So xr of t, the recovered signal, would be the convolution between xp of t, the sample signal, and h of t, which is the reconstruction or interpolation filter we're applying. So in the case of such sinc-shaped filter, we would get x of nt omega ct over pi sine of omega ct minus nt over omega ct minus nt. Why is that? Well, it's because xp of t is made of several impulses. So it's a train of impulses, although these impulses do not all have the same amplitude. The amplitude is given by the signal, by the original signal. And when we do the convolution between all these impulses and the sinc function, you know that the convolution with an impulse corresponds to a shift in time. Therefore, what we obtain in xr of t is the superposition of many replicas of the sinc function h of t. These replicas are all shifted by different quantities, all integer multiples of t, and they're obviously scaled differently, and the scaling factor is given by x of nt. Let's visualize this concept to make it more easy to understand. So here on the right hand side of the slide, you see the sequence of operation I was trying to describe mathematically just a while ago. So at the top we have the original signal, once again x of t. Let's assume it has this smooth trend. Then after we sample it by multiplying it by a train of impulses, by a sampling function, we obtain xp of t. So you see xp of t is a train of impulses, and the amplitudes of such impulses follows the shape of the original signal. Cool, they're all spaced with a period t, which is the sampling period. Once we interpolate or reconstruct the original signal through a perfect filtering, so by convolution with h of t, which is a sinc, as I tried to explain before, we obtain a series of replicas all superimposed, centered at different locations and with different amplitudes. So you see at the bottom right of the slide xr of t, which is obtained by taking these sinc functions, replicating them with different time shifts and with different amplitudes given by the samples. And the result is the envelope in thick black line, which, as you can see, is a perfect reconstruction of the original signal x of t at the top. This is all nice because we see that a perfect reconstruction has been obtained. However, there's a drawback, because such perfect result comes at the cost of using an h of t that is quite complicated. As you can see, realizing such sinc function for perfect interpolation can be quite complicated. This function is non-causal, it is non-zero for negative times, and it is difficult to approximate. So what we will see next are alternatives to obtain not perfect but sufficiently good interpolation through a low complexity approach. Let's give another example for this purpose, which is the zero order hold. So in this case, we will see that we're doing basically the opposite. We're not trying to achieve perfect reconstruction through some difficult interpolating function, we're just using a very simple interpolating function, probably the simplest we can think of. So if your recovering system has an impulse response as the one described on the left of the slide, which is basically rectangular, then what you obtain is the recovered signal at the bottom right of the slide. We call this x0 of t because such recovery system is called a zero order hold. It basically holds the value of each sample until the following one, and then it switches up or down to the next value. So the result is basically a staircase looking function which somehow approximates the original signal. And of course we can see that the finer the sampling has been done, so the more samples we have, the higher the sampling frequency, or equivalently the smaller the sampling period, the better such staircase approximation is compared to the original signal x of t. So in the time domain, what we can say is that this is probably quite simple to implement, but perhaps its accuracy is limited. Let's see the same thing from the frequency domain perspective. From the frequency domain perspective, such rectangular impulse response corresponds to a sinc. So we see the h0 of j omega in the frequency domain, the frequency response of such filter that does a zero order hold interpolation has a sinc structure, and that it is pre-multiplied by an exponential, in this case e minus j omega half t, just because such rectangular is not centered around zero, it is shifted, and this shift in the time domain, this delay, gives you the product by a complex exponential, as you recall from the shifting property. So in the figure on this slide, you see represented the magnitude of the frequency response of such filter, of such interpolating filter. So it's basically the magnitude of a sinc function. And as you can see, its filtering properties are not perfect like the ideal interpolating filter we saw first. In our first example, we consider a perfect rectangular shaped filter that takes the replica we want and cancels out all the other replicas. In this case, we have a sinc behavior in the frequency domain, so there would be some distortion introduced in the original signal because in the pass band the gain is not fixed, it's not flat, and in the stop band, well, there's not really a stop band because the filter doesn't go sharply to zero as the original filter. So the zero order hold can be simple to realize, but its performance might not be as good as we want in certain cases. So can we do better? Well, here we see a third example, which is basically a trade-off between the first two we have seen. So we're trying to do something in between. Again, we're not aiming for perfection, but perhaps we might want to do a little bit better than the zero order hold. So in this case, we do what we call a first order hold or a linear interpolation. This is quite simple to understand intuitively. So let's look at the figure first. We have our sample signal at the top right, all those impulses we are familiar with by now, and we use as an interpolating function h of t, which is the triangle that you see represented on the right. What's the result? The result is basically equivalent to connecting the different samples. You can think about the samples of xp of t and you connect them with a straight line. That's what this system does, and you obtain xr of t at the bottom right of this slide. So this signal again is not quite the same as the original signal, which is at the top right in dashed, but it is closer to it than the zero order hold would be. Cool. What about the behavior in the frequency domain? What do we expect? Well, what is the Fourier transform of a triangular signal? We know that a triangular signal is the convolution of two rectangular signals. Therefore, we know that the Fourier transform of a triangular signal will be the product of the Fourier transform of two rectangular signals. So, because the Fourier transform of a rectangular signal is a sinc, h of j omega for a triangular signal is a square sinc. If we represent the magnitude of a square sinc, we obtain the shape depicted in this slide, and it is compared again to the ideal interpolating filter, which is a rectangular in the frequency domain, and we see that once again its behavior is non-ideal because it is not constant in the pass band and it doesn't go sharply to zero in the stop band. However, it is better than what the zero order hold was in the frequency domain. Nice, let's now see another example to better clarify the role played by the Nyquist frequency. So we're gonna go back with an example to better understand the sampling theorem, both in the time domain and in the frequency domain. So as an example, let's consider a very simple function, which is the cosine of omega 0 t. So our original signal is a cosine of omega 0 t. Cool. We know very well that the Fourier transform of such signal is given by two impulses centered at frequencies plus and minus omega 0. In particular, we know that it's given by pi delta of omega minus omega 0 plus pi delta of omega plus omega 0. You see this represented at the bottom left of the slide. So x of j omega is the spectrum of the cosine, so two impulses. Now let's assume that we sample our cosine signal with a certain frequency omega s. In this example, I'm assuming that the sampling frequency is 3 times omega 0. Notice that omega 0 is the maximum bandwidth, is the maximum frequency of our original signal. There is nothing beyond omega 0. So omega 0 plays the role of omega m at the beginning of this class, if you recall. So if you also recall the Nyquist theorem, or the sampling theorem says that a signal can be perfectly reconstructed if we sample it at a frequency that is at least twice its maximum frequency. And in this case, we're sampling at a frequency that is 3 times its maximum frequency. So we can guess that it will be possible to recover our original cosine. Let's see how. So now we look at the figure at the bottom right, and we see that once we sample the cosine, the effect in the frequency domain is a replication of its spectrum. So those two impulses will be replicated an infinite number of times, and the replicas will be separated in frequency by a quantity omega s. You see this represented in the figure, where the original one is the one in the dashed box, and the other ones are other replicas. So you see that for this particular choice of the sampling frequency, different replicas of the pair of impulses do not overlap. They don't overlap with each other, so that the first replica does not get the original spectrum dirty, and therefore it would be possible, by just filtering, recovering the original signal. So if you imagine to apply the filter in dashed lines, you would eliminate all impulses and you would be left with only the two ones in the middle, the dashed one and the solid one. And if you anti-transform that, well, they are identical to the original signal. So if you anti-transform, you obtain exactly a cosine of omega 0 t. So you obtain exactly the original signal x of t. Let's see the same thing in the time domain. In the time domain, looking at the top plot in this slide, we have the original signal. It's a cosine of omega 0 t. And we have sampled it at a frequency 3 omega 0. That means that for every period of my signal, I have taken 3 samples. That's exactly what you see in the figure. You see there are 3 arrows, 3 deltas for every period of the signal. So the sampling frequency is 3 times the frequency of the signal. Now assume that you only have the samples because you have sampled your signal. So move to the bottom plot. Now if you have the samples and you try to interpolate them through a sinusoidal function, well, what you obtain is the dashed line. And the dashed line exactly corresponds to the original one, which is the solid line on top. So once again, we have seen intuitively the same thing in the frequency and then in the time domain. So in the frequency domain, the replicas did not overlap, and in the time domain, it was possible from the samples to recover the signal by somehow interpolating them. Cool. But is this always the case? Well, no. So now, let's take the same original signal, the same cosine of omega 0 t, which has the same spectrum represented at the bottom left, but let's sample it with a lower frequency. Now the sampling frequency is omega s equal 3 omega 0 over 2, meaning only 1.5 times the maximum frequency of the signal. So again, if we recall the sampling theorem, we know that this will not be enough to recover by any means the original signal. Let's see this in the frequency domain. So let's look at the bottom right. Now, because the replicas after sampling are spaced by omega s, and because omega s this time is half what it was before, you see that some of these replicas do overlap. Basically what happens is that the first replica falls within the spectrum of the original signal. So if you look at the figure at the bottom right, xp of j omega has many impulses, but let's identify what is what. There is an impulse centered at omega 0, and there's another one in dashed centered at minus omega 0. That is the original spectrum. Then there are other impulses, and those are replicas, and some of them are misplaced. In particular, 2 of them fall closer to the origin than the original spectrum, and those 2 are within the dashed rectangular. So if you just try from this sample signal to apply perfect reconstruction with the perfect filter, which is represented by the dashed line, you would cancel every single impulse except the 2 ones in the middle, the solid and the dash ones. But these 2 are not quite the original ones. In fact, these 2 spikes are not at plus and minus omega 0. They are at omega s minus omega 0 and omega 0 minus omega s. So if then you anti-transform this, the signal you have recovered was not the original one. The signal you have recovered is a cosine of omega s minus omega 0, which in particular is a cosine of half omega 0 t. So you have recovered a signal that has nothing to do with the original one. It's also a cosine signal, but it has half the frequency. To better understand this, let's see the same thing intuitively in the time domain. In the time domain, we have again the original signal at the top. It's always the same, it's in solid lines. We sample it again. What's the difference now? Now we're not taking 3 samples per period, we're taking only 1.5 per period. That means that it takes 2 periods of the signal, 2 full oscillations of the cosine, for us to collect 3 samples. So as you can see, the arrows represent the samples, and it takes 2 periods to have 3 such samples. Cool, now assume that you have done such sampling and move to the plot below, and you have the arrows, so you have the samples. And now what you try to do is reconstruct the signal. So you try to interpolate these samples with a sinusoidal wave, and you obtain the dashed one. Right, you have interpolated the samples, you have reconstructed a signal. But is the signal the same as the original one? No, by no means. What we have reconstructed is a different signal. In particular, if you look at it closely, it's also a cosine signal, but it has a frequency that is half. It has double the period and half the frequency. So again, it's cosine omega 0 over 2t. It's not the original signal, and we came to exactly the same conclusion as by looking at the frequency domain. So this confirms and explains and clarifies, hopefully, the importance of the sampling theorem and of the Nyquist frequency. So to wrap up today's class, we have learned how to represent a continuous time signal by its samples, which are its values at points equally spaced in time, and then reconstructing the original continuous time signal from its samples. We also learned under what conditions such reconstruction is possible without losing any information. Such conditions are given by the sampling theorem. In the next class, we will apply signal and system analysis and the tools we have learned so far to study some simple communication systems. See you in the next video.